Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Alhamdulillah, wassalatu wassalamu ala rasulullah, amma ba'du. Alhamdulillah, in this moment we can meet again through the Zoom application to continue our lesson in competitive programming, and we are still continuing discuss about graph, and and start from now. I think our class is more student, right? So welcome ke Mas Hasan, and nice to meet you in our class. We will so happy with your present in our class. So can you introduce yourself to us?
Assalamu alaikum.
Waalaikumsalam.
I am from grade 9 IOI semester.
Okay, grade 9. Okay. That's great. Do you still in junior high school?
Can you ask again?
Do you in junior high school or senior high school?
I am in the combined IOI section with the other seniors.
Okay. Okay, that's great. And then how I call you, Kamas or Hassan?
Whichever you feel easier.
Okay, so let me call you Hassan.
Okay.
Okay. And then, so I think I also have to introduce to you. Let me introduce myself. My name is Abdul Malik Nur Rahman, and you can call me Amnu. So you just call me Amnu.
Okay.
And then I am 22 years old, and I have been participated in IOI in 2018 in Japan. And alhamdulillah I got silver medal. And then in 2019 I participated once again in Azerbaijan, and alhamdulillah I got gold medal.
MashaAllah.
All right, so I hope you all can participated in IOI and then give your best medal to your country. Okay, good luck. All right, and then thank you, Hassan. Before we start our lesson, let's pray together. Allahumma inna nas'aluka ilman nafi'an wa rizqan thayyiban wa amalan mutaqabbala. Rabbana zidna ilma warzuqna fahma. Rabbi israh li sadri wa yassir li amri wahlul 'uqdatam min lisani yafqahu qawli. Amin. All right. After that, let me discuss the new topic that is about MST. Do you know what is MST? It is an
No.
abbreviation.
I don't know.
Okay. Uh, Anyone know? Okay. Minimum spanning tree. That's it. Minimum spanning tree. And the abbreviation is MST. So, do you know about the algorithm to find the minimum spanning tree? All right. Prime. Okay. Is there any other algorithm? Pascal. Okay. That's it. So I think you have ever studying about that. So let me just explain the brief problem about MST. The MST is the MST problem given in a graph. So if there is a graph, it usually weighted graph, right? Or let me find the sample. All right, for example, like this. There is a graph, and then or let's use this sample. Given this graph, and we want to choose some edge in order to connect all of the nodes. So we will take some nodes, for example, any nodes here, so that all of the node is connect. For example, like this. Then all of them is connect. Then our our objective is not only connect all of them, but we will also find the minimum cost of all the possible connection. So of course, this way is not minimum, right? There is another way that will got the less cost from this. All right. So how to get the minimum cost in order to connect all of them? So the algorithm is like this. We can choose the node starting from the cheapest one or starting from the minimum weight. So if we see this graph, the minimum cost is 4, right? So just connect it. After that, where is the next minimum? The next minimum is 5. So we will connect it. After that, the next is 6. And there is another 6 here. And then there is 7. Okay. All right, Hassan. You can still cannot view the screen. So how about the others? Can you see my screens? Right. Let me try another way. How about now? Can you see my screen now? Right. I hope You can see it. Or are you in the same room or in different place? In the same room, right? All right. So you can see from your friend's screen. All right. So I hope the problem will be solved soon. Okay, let's just continue our algorithm to find the minimum spanning tree. So after see we connect 7 here, we will connect another 7, and then we connect 8. But for this edge, we are not, so this edge is not important, right? So we don't connect this, since this node and this node is already connected before. So it is not necessary to connect this. All right, so just leave it unconnected or leave it unchosen. So we will minimize the cost. If we use this, then the cost will be increased, right? All right, and then the next edge is this, the edge with weight 8. But since there's 2 nodes is already connected, so just leave it unchosen, and then we continue to this edge. After that, we continue this edge, and for this edge, it is not important since they are already connected using this way, right? And then let's continue to the next edge, which is 9, and this is not important as well. And then this is also not important, and then 12. Oh, there is also 10 here, but it is not important, and so on. All of the edge is not important now since all of the node is already connected. So this is the minimum spanning tree. That is the tree from a graph so that the total cost is minimum. Let's see, this is the result, the tree we already choose. And yes, this is called as Pascal algorithm. This is called as Pascal's algorithm, and we usually use this in the most problem. We will solve it using Pascal since the implementation is easier if we compare to the Prime's algorithm. All right, then how about Prime's algorithm? So for Pascal, we will see the graph in general, right? But for Prime's algorithm, we will find the minimum spanning tree starting from a node. For example, we will choose any nodes. We usually choose node 1 or first node. And then we start the minimum spanning tree from this node. So how to find the minimum spanning tree? So first of all, we will see all of the edges connected by 1. So there are 4 options, right? And then we have to choose one of them since we have to connect one with any other nodes. So since we want to find the minimum, so we will choose node 6, right? Yes, we will choose the minimum. That's it. After that, we already connect it with 4. After that, we will choose any node that connecting between visited node and unvisited node. So between this, and also this, and this. All right. Which one is the minimum between all pair of visited node and unvisited node? Yes, 4 to 3. The cost is just 7. So we will use this. All right. We will visit 3. After that, which edge is minimum? 3 to 6. That's it. The cost is only 5. After that, which one? 6 to 8. That's it. Only 6. And then, all right, 4 to 7, only 7. After that, which one? 7 to 5. That's it. Only 4. This is the cheapest edge. And then, after that, which node? Yes, 7 to 9 is okay. Or 5 to 2 is also the same. So we can choose one of them. And then after that, the other one. All right, we will cut the minimum spanning tree using this. All right. Which one is easier? All right. What is the complexity? The complexity is around the logarithm e, if I not wrong, or maybe e logarithm v. Yes, maybe it is just the same as Kruskal, which is Kruskal e logarithm e, since we need to sort the edge, right? All right. And then how to prove that this algorithm is correct? This algorithm will achieve the minimum spanning tree of all possible spanning tree. All right. When this is correct, so let's prove the Kruskal algorithm first. In the Kruskal algorithm, we always use the minimum edge. So it is quite intuitive enough to see that is the minimum possible spanning tree, since we always use the minimum cost, right? So after we sort the edge, and we will choose the minimum edge of all of them. So it means we already get the minimum. And we know that the minimum number of edges to connect n nodes is only n minus 1 edge, right? So if we want to connect n nodes, we need at least n minus 1 edges. All right, so if we choose the cheapest n minus 1 edge, this way we'll always achieve the minimum total cost. All right, but how about if there is an edge that already connected by another edge, so we will just leave it since it is redundant, right? So for example, we already connect 5 and 7, so we don't need the edge with cost 8 here. So we will never use this. So just keep it. So we can just remove the edge. So the minimum is still, so we will still use the n-1 minimum edge. All right. This is about Pascal's algorithm. And how about Prime's algorithm? Why this always achieve the minimum cost? So it is because if we start from a node, for example, starting from node 2, then we know that in order to connect all of the nodes, so the second node have to be connected to any other nodes, right? So one of this node should be chosen between 10 or 8. One of them should be chosen. So we cannot skip all of them. If we skip all of them, so the second node will not connect to the other nodes, right? But our objective is to connect all of the nodes. So we should choose one of them, or even both of them is okay, but don't skip all of them. All right. So since we know that we cannot skip all of them, so we have to choose at least one. Then in order to achieve the minimum cost, we will choose the cheapest one. All right. It means 8 should be chosen. And then after that, after we connect 2 with 5, we know that 2 with 5 will should be connected with the other nodes, right? We cannot skip all of these nodes, sorry, all of these edges. So we will choose at least one of them. So because we choose one of them, so we will choose the cheapest one, which is 5 to 7. All right. After that, after we connect these 3 nodes, we shall connect them to the other nodes. We are not allowed to isolate them, so they should be connected with the others. All right. Then we shall choose between all of these edges, right? We cannot skip all of them, so we will choose at least one. Since we should choose at least one, so the optimal ways is to choose the minimum one. All right, and so on. We always choose the minimum between all the edges, so it will achieve the minimum cost of all the possible spanning tree. All right. Is it understood? All right. Is there any other questions? All right. Then how to implement the primes algorithm? Or before that, the easier one, can you implement the Pascal's algorithm if you ever implement it? All right, that's great. Just sort the edge, right? And then what data structure result we is that's it. Disjoint set union. So we will use disjoint set union in order to check whether a pair of nodes already connected or not yet. Okay, that is the Kruskal algorithm. All right. Maybe some of you can you implement the Kruskal algorithm? Yes, all right. Let me share the link again so you can join the code interview page. All right, we can use vector of vector, or sometimes we also use vector of pair. Yes, just like this. I think we should store triple since the graph is weighted. After coding the Kruskal algorithm, then output the total cost. All right, let's see one by one. Of course, we solve code get function since we need disjoint set union. And then since we need disjoint set union, so we solve reset the graph, right? How to reset the graph? Yes, we solve iterate for all nodes. The parent of each node is itself. All right. And then we can push back each edge and we should put the weight into the first, right? Since we want to sort based on the weight. All right. And then we will check one by one. But not that the vector is zero base, right? Starting from zeroth index. So the iteration also should be zero base. And then we will check whether they are connected or not. If not connected yet, then just connect it. Yes, this is the way to connect it. And the complexity is just O1, O1 amortized. So this is quite fast and so fast actually. This is just O1. And then since we use this edge, so let's add the total cost by the weight of this edge. All right, this is correct. After that, yes, we have to reset the disjoint set union. Maybe if you start from index 1, then this is will be less than or equal. I think. And then actually, in order to join them, parent A equal to B, we can just make it B. Even parent B is also correct. All right. That B is simple. And then we solve call the init function, right? When we call the init function. All right. Init, and then we will push all the edge and always set the weight as the first element. All right, this is correct. How about this? I think uni solve has two parameters, right? Yes, okay, just remove it. All right, and we also can remove the bracket since it is redundant. All right, if we success the union, then add the weight. I think we should reset the parent before we connect all of them. So before we connect the graph, Let's reset the graph. Right. Yes, this is the way to reset the graph. Just like creating an empty graph, right? All right. After that, how about this? Yes, I think it is also correct. Okay, this is, I think we don't check whether this is visited or not, but we should check whether they are small or not. Okay, there is a question from Ian. Sorry, Ian, which lines of our code? Which lines do you mean? Right. This is not about visited or not, and we don't care whether they are visited or not, but we need to check whether they are in the same component or not. So we will check like this. If they are in not one connected component, so just join them. Okay, and then push. If we use this edge, we can push back to the list of chosen edge. All right. Is there any question? Instead of just join set union, is it Prime's algorithm? Yes, if we use Prime's algorithm, then we don't use disjoint set union. But if we use Pascal, then we need disjoint set union, right? If we only store the set of edges or the current MST, then we don't know whether they are connected or not. For example, this is already visited and this is already visited, but we still need to connect them. But for this case, this is already visited and this is also, but we don't need to connect them. All right, after this, I will show you the implementation of Prime's algorithm. And about Ian's question, yes, if we reset a graph, we just need to reset until the number of nodes, right? No need to reset the whole array. Why? Because just what Hayan said, this will causing time may be exceeded when the number of test case is so big, but all of the nodes is just small. So if we just reset the curve based on the number of nodes, then don't worry, the total node is not greater than some value. But if we reset until the maximum n, so if the number of test case is so big, so our complexity will be t multiplied by the maximum n, and this is causing time limit exceeded. Okay, so so just reset only until the number of nodes, just like when we do memset for specific array, right? Please don't do memset when there are too many number of test case, but just iterate it from 1 to n, and then we reset it manually. All right. Yes, heap is also the same as priority queue. We just need to use priority queue in order to find the minimum between all of them. Actually, Prime's algorithm has two types of implementation. The one is just like Dijkstra algorithm. Do you know how to implement Dijkstra? I think we already discussing in the past meeting, right? So the implementation is just like the Dijkstra algorithm, but the pair we push into the priority queue is different. In Dijkstra, the first value is the length of the path, right? But for Prime, we only push the cost of the edge. So we just push the cost of one edge, not the whole path. All right, the difference is only here, and the other is quite same. And for this implementation, the complexity is a logarithm p. And how about the second algorithm? The second algorithm is just brute force, just like brute force. And then the complexity is of v squared without logarithm. All right. When we use this, we will use this when the curve is complete curve. Do you know what is the complete curve? Yes. What is it? Or how many edges in complete curve? That's it. The complete curve is curve with all vertices. All pair of vertices is connected directly. That's it. And the number of edges is n combination of 2, which is n times n minus 1 divided by 2. And this is around n squared, right? N squared divided by 2. All right. So if we want to find the minimum spanning tree in complete graph, so if we use Prime's algorithm or Pascal algorithm, then the complexity is around v squared logarithm, right? And also about Prim's algorithm, the complexity is also the same. But if we use the second implementation of Prim's algorithm, then the complexity is smaller. So this algorithm will be faster. All right. So that's why when we implement Prime, we should use this, because if we use this, then the complexity is just the same as Craskell. So we usually use Craskell instead of Prime, since the Craskell algorithm is easier to implement. All right. So there are two ways to implement Prime's algorithm. The first one is Dijkstra, and the second one is brute force. Not Dijkstra, but just like Dijkstra, but we just push the edge here. All right. So I hope you already know it, how to implement Prime's algorithm in the first way. All right. How about the second way? We can use brute force. How to implement it? Let me show you. In order to implement Prime's algorithm, we have to store the adjacency matrix. So the graph will be like this. We will store the adjacency matrix. All right. And then we also need to store the minimum weight. Yes, we also can use adjacency list, but this is when we want to implement it in OP squared. So there are two ways to implement Prime's algorithm. This is the second way, and the first way is just like Dijkstra. If you want to use the first way, then we need to store the edge in adjacency list. It is easier to implement with adjacency list. All right. And how about Craskell? We need to store it with edge list. So we just need to store, for example, pair of integer and pair, since we need 3 values. All right. So the graph representation is different. This is edge list and this adjacency list. And the third way is adjacency matrix. This is used when the graph is complete. And Craskell algorithm used when the number of node is around the number of edges. So the number of nodes and the number of edges is not too different. For example, there are 100,000 nodes and then 200,000 edges. So we will use Craskell for this way. And we rarely use the first Prime's algorithm, since Crucial is more easier to implement. But when we face the complete graph, then the second primes algorithm is faster than Crucial. Since Crucial need e logarithm e, and primes only need e without logarithm, or actually v squared without logarithm. So this is faster. All right. Then because we are solving in complete graph, so it is better to use adjacency matrix. If the input is still edgeless, then we have to convert it in this way. All right. And for minimum spanning tree, the graph is undirected. All right. And don't forget to make the initial value become infinite. Okay. Then we will store the array of Boolean in order to check whether the node is visited or not. Just like the first primes algorithm, we also need to store visited or not, right? This is just like Dijkstra algorithm in implementation. And then let's start with the first node. Let's visit the first node, and then the minimum value for its node equal to the cost if we want to connect from 1 to I. All right. After that, we want to visit n-1 other nodes, right? Since we still visit one node and we need to visit all of the nodes, so we need to visit another n-1 nodes. Which node we have to visit? We need to choose the minimum cost, the node with the minimum cost. So we will find the minimum one. We usually use this. Let minimum 0 is infinite. Then let's iterate for all nodes. If a node is not visited yet, and the cost, or let's name it cost, and this is the minimum. If the cost to connect J is cheaper than the cost to connect the minimum, so the minimum becomes J. All right. So after that, we already know which node is the cheapest one, which is the node with index mn. So we will visit it, and then we will update all of the costs. Right, cost j is the minimum between cost j and weight between mn and j. All right, this is how to implement the minimum spanning tree using Prim's algorithm. And don't forget to add the total cost. All right, this is how to implement Prim's algorithm to solve a complete graph. Is it understood? Okay, then what is the complexity of this implementation? Yes, p squared, the number of vertex squared without logarithm, right? So this is faster than Pascal when the graph is complete, and even faster than the first prime algorithm. The first prime algorithm is using priority queue, right? Priority of pair, and we will choose the minimum. And then just like when we implement Dijkstra algorithm, right? We will start from a specific node, and then we will push all the adjacent from node 1, right? Pascal more faster when the number of node and the number of edge is not too far. Okay, so just see the constraint. If the constraint is, for example, like this, then just use crosscalls. But if the graph is complete graph, and then the graph is complete, so it means the number of edge is around v squared divided by 2, right? So it is faster to use Prime's algorithm. But don't use the first Prime implementation, but use the second implementation. All right. Here is a sample problem which we need to use Prime because the number of edge is too big for complete graph. I think the problem is from SPOC. All right. Then you can solve it using Prime's algorithm. Since the time limit is too strict, it is 100 milliseconds. All right. Okay, maybe let me finish this. We need to push to the priority queue the value of x, but we should put the weight in the first value, right? So when we input the edge, then we should push the weight first, W and then V. Okay, so just continue to implement the primes algorithm. When PQ is not empty, then we will choose the cheapest one, right? And then we should check whether X is visited or not. If it is already visited, so just continue it. But if not visited yet, then we will visit it. After that, we will iterate all of the adjacent from x dot second, and then just push to the priority queue if it is not visited yet. If it is already visited, then it is redundant to put it on the priority queue. All right, this is the way how to implement the primes algorithm, but with the complexity just same as Kraskos. And how do you think about these two algorithms? Which one is easier to implement, Kraskos or primes? Yes, I think so. I always use Kraskos if the graph is regular. That's it. But when the curve is complete, then it is better to use the second primes algorithm. It is if the time limit is too strict. But if the time limit is loose, then we also can use Pascal as well. Right. Is there any other questions about this? Okay, that's great. Then let's continue discussing some problems about minimum spanning trees. For example, let's start with with this problem. Okay, I think I have to invite Santun the to our widgets group. So let me make it public. Please apply to this widgets group, and then I will accept you. Alright. Problem is like this. Given a weighted graph, weighted undirected graph. So let's draw the graph. Right. If you want to build the minimum spanning tree in this graph, and then we will connect them. Okay. Then the minimum spanning tree is 9. Okay. And then in order to make the minimum spanning tree is different, so we need to increase some value from 4 become 9, sorry, become 6, from 3 become 6, and then from 2 become 6. So the next minimum spanning tree will be like this. The minimum spanning tree will be different. All right. For the second case, since the number of edges is only 4, so we cannot change the whole edge, right? Okay, let's see like this. The curve is like this, and the cos is like this. Okay, Okay, all right. Let me invite you. Please accept my invitation, and then you can see the contest. Okay. We know that the initial minimum spanning tree is here, and we cannot remove both of them. If we remove both of them, then we cannot make the minimum spanning tree, right? Okay. For the third sample, we will connect this. Okay. For now, do you understand the problem? All right. And then, do you have any idea to solve this? Which algorithm we will use? Yes, just use crosstalk. And how many times we need to do crosstalk algorithm? Yes, twice. Since we need to find the first minimum spanning tree, right? After we got the minimum spanning tree, then we will find another spanning tree without using this edge. So we will use different edges. All right. For example, like this. We will create the second minimum spanning tree using the other edge. After we cut the cost of its minimum spanning tree, for example, the first minimum spanning tree is A, and then the second minimum spanning tree is B, then what is the result? Do you know what is the answer? I think not only B minus A, since for this case, the second minimum spanning tree is 15, and then the first minimum spanning tree is 9. But the answer is not only 15 minus 9, right? The answer is not 6. So what is the formula? Not only P minus A, but it's true. For example, the maximum of the first minimum spanning tree is C, and then the maximum minimum spanning tree for the second case is D. Then what will be the result? What is the result? This is the total. This is the maximum. This is the first MST, and then this is the second. And how do you think? Let's make the formula of the answer. Is it 3 plus 1 times the number of edges minus 8? Is correct or not? I don't think so. What if the first sample has weight like this? This is 2, 3, and 4. And then this is 5, 6, and 7. So the first minimum spanning tree has cost 9 with the maximum is 4. And then the second minimum spanning tree is 18 with the maximum is 7. Then should we increase all of them become 8? The correct answer is we should change it into 7, and then we should change it into 8, and then change it into into 8, right? Not all of them 8. Do you agree with this? Is this minimum, or can we make it cheaper? If you make it 7, then the tourists may connect this. Okay, so please make it 8 in order to avoid using this. And also about this, if we make it 7, then we can use this. So please make it 8. But for these nodes, we should not make it 8, but make it 7 is enough. Why? Because we will never use it. Okay, if we already connect it and also this edge, then this edge is redundant, so we will use this edge. Okay, so just make it 7. Right. So the solution is like this. After we create the first minimum spanning tree and storing which edge we will use, then we will create the second minimum spanning tree and then make the tree from it. Create a tree from the second minimum spanning tree. After that, let's use the first minimum spanning tree and try to connect in the second minimum spanning tree and try to find the maximum maximum edge in this path. Okay, you got it. So after we find the first and second minimum boundary, for example, like this. After we sort the adjacency list in Kruskal algorithm, we will iterate it one by one, right? For example, let's iterate all the edges, and then we want to check whether they are connected or not. If they are connected, so for example, like this, let's make it W and U and V. If this is not equal, so we will connect it. And then we will remove this edge. Or let's store the vector of the first MST and the second MST. So this is stored in the first MST. Okay. And then I think we solve back to this one union. Okay, maybe I need to implement the full algorithm. Let me input all on the value. And then we will push into adjacent series. Okay, I think we should push to the edge first. Okay, please wait. Okay, let me continue. After we push the adjacency list, and then we will sort them. After that, we will iterate one by one. Let me iterate this thing this way in order to store the array of Boolean, store the index of the edge, and then we will connect it to reset the parent first. After that, we will push all of the edge in the first MST. Maybe we should push the weight as well, or just push its I. All right, this is MSTA. And then after we get the first minimum spanning tree, we will find the second one using like this. Please check first whether this is used or not. If it is already used, then just skip it. We will not use this anymore. And once again, we will reset the minimum spanning tree. Is the cities and road always connected? We want it to be connected or not? Okay. Then if it is not used yet and it is not connected yet, then we will use this. And then we will push to the adjacency list, I think. All right. For the second minimum spanning tree, we will use adjacency list. After that, we will check whether all of the nodes is connected or not. If they are not connected, then just output -1, right? So we cannot create the second minimum spanning tree, right? So if get I is not equal with get 1, then just see out -1. Okay, you got it? Why we check this? All right, then let's continue how to find the minimum cost. The minimum cost is like this. Let's create the second minimum spanning tree. So for example, the minimum spanning tree is like this. And then the first minimum spanning tree is, let me use red. Okay. For example, the minimum spanning tree is this tree. There any cycle here? Okay, I think, okay. The red is the first minimum spanning tree, which is the cheapest one. And the green is the second minimum spanning tree. So if we want to avoid the first minimum spanning tree, and we will use the second minimum spanning tree instead of it. So we need to make the cost of the red nodes become greater than the path of the green edge. Sorry. For example, like this. For example, the weight of this is 2, and then the weight of this is 4 and 5. Then we should make it 6. Do you know why? Okay. Yes, that's it. Because if we make it 6, then when we create a spanning tree, then this edge will not use. But if we make it 3, then this edge is still used. Or 4, this is also still used. Even 5, we can use this in the alternative of this. All right, so we should make it 6. All right, so this is the minimum cost. For the other case, for example, for this case, if the weight is 1, then we should make it 8, since the path between these nodes is 8. All right. And the other thing, for example, if you want to connect this, and initially the weight is 4, then we should make it 7. All right. Did you understand about this? Then the question is how to find the maximum in any path, in some path. Do you have any idea? Using which algorithm? Do you know about, do you know the algorithm to find the maximum between any path? For example, like this. For example, there is an edge between this node and this node. So the cost of this will be updated, become the maximum between this path, right? Is it true? Okay. Then how to find the maximum weight in a specific path? Do you have any idea? All right. Do you know about LCA? Yes. Then we can use LCA, uh, lowest common ancestor. How to use it? Yes, if we want to find LCA, we should use first table, right? For example, we will create the sparse table like this. Uh, I should make it ANC, which means ancestor. And we'll use lock here. All right. And for this case, we need to store the maximum of pet, maximum of weight in the pet. So let me do JFS first in order to create the tree. Let me make the GFS algorithm. This means the direct parent of X is P. Or just make it like this. Adjacent means the second minimum spanning tree. So we will set the ancestor of Y second is X. But if Y second is equal to P, then continue it. After that, sorry, this is the direct parent. And then the path between them is just Y first. All right. And then just do GFS. To the Y second and X. All right. After we know the parent of its nodes, then we can compute the sparse table, right? What is the value of N and M? 2 to E5, and then we should take the logarithm 18, I think. 2 to the power of 18. All right. So we will create the LCA here. I think we haven't discussed about LCA, right? Haven't discussed it before, but maybe some of you already understand this. So the ancestor will become like this. All right. And how about pet by j means the maximum between the pet of this and also the pet of this. All right. Anyone have a know about LCA? Pet means the maximum weight. Sorry, the maximum weight if we want to jump from I to to the power of I. Sorry, from j to the power of I. What is the maximum weight between all of these nodes? All right. But you already know about ancestor, right? All right. So the algorithm for ancestor is like this. In order to jump to the power of I from j, we need to jump to the power of I minus 1, become ancestor I minus 1j, and then we jump again to the power of I minus 1, right? Okay. And then from the definition of the path, the definition of the path is the maximum weight between them. So the maximum weight between all of these edges is the maximum between this and this. Okay. The maximum between all of the edges here is path I minus 1j. All right. Okay. And the maximum for all this path is path I minus 1, since we want to jump to the power of I minus 1. Then start from which nodes? Start from ancestor I minus 1j. Okay. That's great. Okay. So let's continue iterating for its first minimum spanning tree. I think we just need to make it MSD. We have to iterate all of the MSD, right? And then let's make it U, V, and Y. Y is equal x dot first, and then U equal to x dot second dot first. This is x dot second dot second. After that, let's find the maximum between U and V. So the answer will be added by, let's make it query U V plus 1 minus Y. Then we will see out the answer. All right. You got it about this trick or this formula? Okay, then we have to find the we want to solve the query function, right? Void query. Sorry, not void. This is integer. from two specific nodes. So I think we should store the depth of each nodes, right? In order to find the LCA. So we need to store the depth. The depth of E dot second is equal to the depth of x plus 1. All right. So when we try to query this, we will check which depth is greater. If the depth of x is smaller than y, then just swap it. After that, let's jump from x to until the depth equal to y. And so on. I think I have to explain you about the lowest common ancestor in the next meeting. So I think we have to finish the class now, since here we okay, you already know. That's great. Okay, so I think we have to end our meeting for now, because in my country it is already master here, and you have to have a lunch, right? So let's close our meeting by praying. Subhanakallahumma wa bihamdika asyhadu an la ilaha illa anta astaghfiruka wa atubu ilaik. Assalamualaikum warahmatullahi wabarakatuh. Yes, please try to complete our code.